Great. It looks like there's a great audience. We have 21 people now online. All right, let me kickstart the defense. So good. I don't know if this is good afternoon or good morning. It's people everywhere. Hard for me to figure the time. But anyway, a good day, everyone, for coming to the Ph.D. thesis defense of Maruan. Today, he is going to talk about the principles of learning and in multitask setting, a probabilistic perspective. We have an excellent thesis committee here. We have Ruslan Salakodinov from CMU. We have Rich Caruana from Microsoft, and also Amit Talwalkar, also from CMU, and also Peter Abil from UC Berkeley, and Eric Xing from CMU. Just to speak briefly about the process here, we're going to have Maruan to present the thesis, maybe in about for about 45 to 50 minutes, I guess. And then there will be a short kind of open session for the audience to ask questions. And then the thesis committee will be taking turns to ask questions publicly, to Maruan. And then after that, there will be a short closed door session to discuss and make decision about the outcome of the defense. And during the presentation, for the sake of flow and clarity, please refrain your question only to clarification ones. And if you want to discuss technical points in a detailed fashion, please wait until the finish of the presentation to enter into that phase. So with that, Maruan, floor back to you.
Thank you, Eric. Thank you for the introduction, and thank you everyone for coming today. I'm very excited to be at this point of my PhD to talk to you about my thesis, and in particular about the probabilistic perspective on solving various multitask learning problems. So to motivate my research, I like to think about the progression of complexity of different learning problems that we're increasingly able to solve using machine learning. We can depict this progression on a chart where the x-axis roughly corresponds to time, past, present, future, and the y-axis corresponds, figuratively speaking, to the complexity of a problem that can be solved with machine learning. And over the past decade, we witnessed that certain forces such as data, compute, software, as well as algorithmic design have been pushing this frontier towards more and more complex problems. And along the way, we can roughly depict some of the achieved milestones on this chart. And again, roughly, it's figuratively speaking. But what we're able to essentially solve today with machine learning, we're able to leverage a couple of principles. We figured out how to do that. Firstly, we figured out how to precisely formulate machine learning problems for which you can collect massive amounts of data. And secondly, we found a way to learn models from these massive data sets that generalize to unseen data from the same distribution. So this is the state of machine learning today, but where we want to go, or where we want to get into the future, is to be able to use machine learning in significantly more complex scenarios. We'd like to be able to build autonomous systems or highly personalized human AI systems, where once our models to be able to operate in complex, dynamic, and rich environments, be highly personalized, be very multi-purpose, and actually liberate ourselves to some extent from having to learn from massive data sets, be able to essentially learn from small data if possible. Now, this is a very ambitious plan, and the whole research community is tackling it. And in my research, I'm looking just at a single dimension of this complexity, from simple to complex. So specifically, I'm looking at the dimension of single task to multitask. And on the far left side of the spectrum, just to give you a couple of examples, we have standard problems such as a single domain, stationary, classification problems of images or text, while on the other hand, on the far right side of the spectrum, we have complex scene understanding, open-ended dialogue, etc. And these are unsolved problems today. So really the question that I'm trying to ask is there a set of principles we can follow when designing algorithms for these complex multitask settings? Now, when thinking about different ways to attack this problem, I like to think about different components of modern machine learning, which is essentially data, models, loss functions or objective functions, and learning algorithms. Now, there's a lot of recent work in the community that's saying that essentially data is all you need. Collect more data, augment the data, the results are going to be great. And there's a lot of interesting line of work in that direction. In fact, showing that using just simply focusing on the data can go a very long way. Now, the majority of research today, I would argue, in the community is focused on big models. How can we design different neural architecture that are able to scale? And there is certain types of neural networks that different authors claim that is essentially all you need to be able to solve machine learning. And of course, there is optimization algorithms, and in the optimization community, stochastic distributed optimization is essentially right now is the master algorithm that is used to train big models on large data sets. Perhaps a little, tongue-in-cheek, but not really. We can follow this deduction a bit further and realize that what we really need is potentially just having a lot of resources or a lot of money so that we can collect large data sets, train big models on very large clusters, right? And this is the current narrative that majority of the community is pursuing, but some aspects of this component of machine learning are being overlooked. And in particular, my research focuses on loss functions. So I should say there is some work on designing different loss functions for different problems, but it's not as popular as focusing on other components. So in this thesis, I will argue that, well, first of all, it's not going to be all you need. Of course, we'll need other components as well, but having design principles for objective functions suitable for multitask learning can be quite useful. I will also touch upon the learning algorithm aspects and show that in certain settings, distributed optimization may not be the right answer or the best answer or the best approach. All right, so with that, now the core of my thesis can be summarized by two claims. So the first claim is that many complex learning problems can be broken up into multiple parts. And these parts, which I call tasks, can be represented with probabilistic graphical models. Now, secondly, using a joint probabilistic model, we'll be able to describe these tasks and model them and derive objective functions as well as learning algorithms that will have interesting generalization properties that we'll be seeking in different multitask settings. Now, this is a very high level description of my approach. And in order to sort of illustrate and support these claims, I structured my thesis in the following way. So at the center, there will be a probabilistic multitask modeling framework, which I will pretty briefly describe and spend most of the time in the talk today discussing various case studies and results that illustrate essentially the same approach, but in a variety of different applications and domains. Each of these case studies is sort of an independent vignette that appeared previously and was published in a peer-reviewed venue. And my thesis has a separate chapter for each of these case studies where we expand on and sort of elaborate a little bit more. So before diving into the framework itself, we need to define what a learning task is, because if we're dealing with multiple learning tasks, we first need to know what each component means. And the goal of learning really hasn't changed since the inception of statistical learning theory in late 60s, which defined learning as discovery of functional dependencies from data that can generalize to unseen data from the same underlying distribution. So essentially, we can define a learning task with three elements: the space of possible inputs and outputs that define a function, a loss or utility objective that plays the role of a quality measure of the function that we're looking for, and finally, a fixed underlying data distribution that we use to define generalization. Now, just to give you a couple of examples, again, standard classification where we have a fixed data set and fixed distribution over different classes, and we're trying to learn a predictor that essentially maps some high dimensional inputs such as images to classes such as cat and dog is a standard learning problem. Similarly, in a stationary environment, we're training an agent to act and maximize its rewards. We're essentially learning a function that maps states to actions, which is known as policy, which is also a standard simple learning task. Now, we will not say that more complex learning problems are these standard learning tasks, but rather we'll approach them as compositions of learning tasks. And the reason is that oftentimes in these more complex scenarios, some of these assumptions will be violated. So by collecting more data, it is rarely the case that we can simply scale the same approach in order to be able to solve the problem in its entirety. Now, how do we represent multiple learning tasks? Once we have these tuples of input-output spaces, distributions, and loss functions, what we propose is first, we can represent each task individually with a probabilistic graphical model. And throughout this talk, I'm going to use factor graphs that are depicted on the slide, where variables are represented with circular nodes and functional dependencies are represented with these little squares, which are called factors. Right? And each factor can have an arbitrary functional form. So these days it would be a suitable neural architecture. And finally, each task essentially is represented by a conditional distribution of outputs given the inputs. And the form that we can use in this case is the Boltzmann form of the distribution. Well, how do we put them together? Well, we can simply take all these graphs and combine them into a joint graphical model. And to do this, we're going to use a very simple approach. We're going to merge the common random variables together and simply replicate the factors. And so as a result, we can define a joint probability distribution using this new graphical model over all the outputs given all the inputs. And of course, we'll have to somehow merge the parameters of all these models, right? And I'm going to come back to this later on. So why is this approach better? And what does it give us? What is the advantage of this approach? Instead of describing it in a sort of abstract way, I'm going to dive right into the first case study here, and we'll focus on the problem of multilingual machine translation, which is a very simple, sort of isolated problem that allows us to understand the advantages of our approach. So in machine translation, we're interested in building models that are able to translate between sequences of words or tokens written in different languages, for example, English and French. And if we take a supervised learning approach, we'll need some training data set of parallel sentences. So we'll need to learn two models, one for each direction, translation direction. Now, if we have n languages, unfortunately, we'll have to learn a squared number of models, right? And just training a single strong bilingual neural machine translation model often requires a lot of data and a lot of compute. So training n such models independently becomes extremely hard or infeasible. And to make the matters worse, typically, we don't have data for all translation directions. We are always limited to some, resource-rich languages. And most of the directions lack parallel data, so we call these directions zero-shot. So in this case study, I will show how to leverage our joint probabilistic modeling framework in order to design loss functions that enable zero-shot generalization. Now, to make things a bit more concrete, I'm going to focus on the simple example of 4 languages: English, French, Spanish, and Russian. And on the left-hand side with this, we have the so-called translation graph, where nodes correspond to languages, edges correspond to translation directions. It's very intuitive. And some of the solid edges correspond to so-called parallel corpora, or the data that is available, supervised data that is available. Now, some of the other edges that are dotted red are zero-shot directions, or directions for which we don't have data. And again, our goal is to train a single model that will be able to translate between all pairs of languages, but while being trained only on the supervised directions only. So we don't have access to the zero-shot directions data at all. Now, the standard approach in machine translation, it's de facto standard right now, is to use an encoder-decoder architecture, right, where the encoder takes as input some sentence and then produces intermediate representation, which is further used by the decoder to decode the sentence in the target language. A team from Google further extended this architecture to multilingual translation by a simple trick. So they decided to reuse the same model for all the translation directions, but indicate to the model which direction it is supposed to translate by adding just a single token that indicates the target language we're translating into. This entire model is trained by simply optimizing the following loss that is given on the slide, which is the negative log likelihood of the target sentence given the previous sentence. The parameters are shared across all directions. The inner sum is the sum over parallel data, and the outer sum is the sum over the supervised directions. Now, the architectures have evolved over the last few years, and now we have very powerful encoder-decoder networks based on transformers. But the loss function is actually pretty simple and has been the same, has been originally introduced in mid-70s and late 80s, and known as pseudo or composite likelihood, which essentially means that from a probabilistic perspective, we take a bunch of independent models or conditional probability models and just treat them as independent problems. And the only way how things are shared between these models is just through parameter sharing. Now, this is great, but and this approach, in fact, surprisingly had some interesting results. So I'm showing here a result on Europarl datasets for this specific architecture and trained on 250,000 parallel sentences. And we can see the performance in the first column. The performance is on the supervised directions, which are English, French, French, English, English, Spanish, Spanish, English, and the performance on the zero-shot direction. So we quickly notice that the model, through this parameter sharing, is able to pick up something from even for zero-shot directions, even though there is no data available. Now, if we increase the amount of data, we see the consistent improvement in performance on the supervised directions. At the same time, the improvement on the zero-shot direction sort of stagnates and sort of behaves inconsistently. So that indicates that potentially this is not the loss function that would want to optimize in this setting. Now, how can we address this? Let me build the joint probabilistic graphical model as I just suggested for the specific setting step by step. Right, so let's imagine that we have a pair of languages for which we observe the data, and the other two languages are unobserved. On the right-hand side, I'm going to build a factor graph, and for this pair of languages, we'll have two factors that indicate essentially that represent the conditional distributions for translation from English to French and from French to English. Note that these factors share the variables that we merged together. Right, there are, of course, unsupervised directions for which we don't have data, and we also have to represent them as factors in the joint probabilistic model. Now we can write down the likelihood, right, for this probabilistic model, which is given on the slide. Now it's going to be a log sum of some probabilities, and note that in this objective function, not only these two factors for which we have data play the role, but also all other factors also participating. Now, importantly, we can prove that minimizing this loss necessarily implies improvement in performance along all translation directions, including the zero shot. So we'll call this property zero shot consistency of this objective function. So I should say that intuitively, optimizing the standard loss or the pseudo likelihood does not guarantee zero shot consistency. And it's easy to see because the loss is absolutely insensitive to the performance along any other directions besides the supervised ones. Now, the challenge here, though, is that to compute this L star, which is the ideal objective, right, is hard. It's impossible because of this inner sum. So we need to come up with a computable and efficient approximation in order to be able to do this. We're going to derive this approximation in this slide. So first of all, we can represent explicitly with this, expand the sums and sort of represent explicitly the products of all these components, where each component is essentially corresponds to this one of these factors, right? And what I suggest here is that we can drop, in fact, most of these components. We don't really need them, and focus only on the components that correspond to translation from English and French into Spanish, and from English and French into Russian. Right, so as a result, we can get the new likelihood objective, which we call agreement-based likelihood, which essentially drops all other terms. And after a little bit of rewriting, we see that we can combine and get two terms that encourage agreement of the model on latent translation into Spanish and Russian. So we still have these sums over possible Spanish and Russian sentences that are intractable, but we can lower bound this objective, and we can lower bound this objective and get to a computable form where we use expectations. Now, the main takeaways from this exercise is that the new objective, which is called agreement-based likelihood, first of all, is computable and can be optimized very efficiently with stochastic optimization techniques. And second of all, we prove in the corresponding paper that it is indeed zero-shot consistent, which means that by optimizing this objective, we necessarily will improve our performance on zero-shot directions. All right, so there's multiple results, and we test this approach in multiple data sets. I'm not going to go into the computational details, but I'm going to just highlight the same example that I just gave you on Europarl with 3 languages, English, Spanish, and French. And the baseline model in this case, right, improves as we increase the amount of data in terms of test performance, as the amount of training data is increasing, but the zero-shot performance sort of stays flat. Now, if we use the agreement-based loss, and after a little bit of fine-tuning, we notice that, well, our supervised directions suffer a little bit, but we have to pay some price by making the model attend to these additional directions. But at the same time, there is a significant improvement on the zero-shot directions, where we not only try to sort of bridge the gap between the supervised and zero-shot performance, but we also see consistent improvement as we increase the amounts of training data. Right. So the same results are visible on many other data sets. And here I'm just going to summarize a few takeaways before moving on. So we started with a question: what does a joint probabilistic model of a fixed collection of tasks give us compared to different heuristic objectives? And the answer is consistency. So the resulting modeling approach is much more consistent than just trying to design loss functions that are sort of simple or easy to optimize. Now, maximizing the likelihood of the joint model is superior to optimizing heuristic objectives. So we get better generalization, but also joint likelihood is an idealized objective. Because of these latent variables, unfortunately, optimizing it directly is often intractable. So the major research effort, if we take this direction, the major research effort goes into sort of finding this tractable approximation that preserves the desired properties of the objective, of the idealized objective function. Now, finally, the methods that I just developed are not just limited to a multilingual translation. In fact, it can be applied to any learning problem that involves multiple data modalities. And specifically, I want to highlight some work, some recent work by other researchers in the computer vision domain that use very similar principles and apply them to multitask learning for vision. Now, before moving back to the actual framework, I'm going to just highlight a few results from another case study where we also had to deal with a fixed collection of tasks, right? But sometimes we don't know which tasks there are. In translation, we knew specifically that there are 4 languages, there are 12 different translation directions. So this is what we're interested in optimizing for. Sometimes tasks may not be given a priori, and we should be able to decompose the problem into the number of tasks given the data that we have access to. So we'll look at this scenario in the context of model interpretability, and we take I would say, non-traditional take on model interpretability. So our motivation was the following. So today we often have access to large data sets, and would like to learn predictive models such as classifiers for these data sets. Now, in order to be able to learn an accurate model, we need a rich enough class of functions that are able to represent a lot of complexity of patterns in this data, right? And one way is to build a very large and sort of expressive model. Unfortunately, this will hinder interpretability. So another way to go is potentially to build a model, sort of a set of models, each of which corresponds to a subset of the data. So essentially, we can take the whole data set and decompose it into different tasks. And we're going to say that each subset of the data in our data set corresponds to a particular task. And each of these tasks can be solved with a simple predictive model. So this is the approach that we're going to take in this case study. And we're going to we'll try to sort of automatically discover how to decompose the model, so the data into disjoint subsets of tasks. Now, the approach that we're going to take, or that we took in this case study, is called contextual explanation networks. And initially, I'm just illustrating the graphical representation of the predictive problem, prediction problem that we're trying to solve, right? The standard approach is based on learning a single functional dependence that takes all the inputs and tries to produce an output. And just for the sake of this case study, we consider that inputs can be separated into 2 disjoint subsets, some of which are high-dimensional features, and some of them are interpretable features. And what we would like to do, we'd like to be able to interpret predictions of our model in terms of the interpretable features. So the approach that we take here is pretty simple. Instead of fitting a single function to this data, we can decouple this function into 2 functions, one of which is going to be complex and one of which can be very simple. So the complex function will process very complex high-dimensional features and output a vector, which will be used as parameters for a simple model. Get my slides one up. Okay, so the predictive distribution under this new model that I showed you on the slide is given on this slide, right? And we have to integrate out these latent parameters that are sort of sample specific in this case. So essentially, what the model does is that it processes the high dimensional inputs. It will generate a distribution over parameters, and for each of these parameters, we can fit a simple model that will make a prediction. Right, so it's very similar to mixture of experts models, but in this case, we'll make further approximations. So in particular, just to give you an example of how it looks like in practice, let's say we're working in a medical domain. We have patients with CT scans or medical images, as well as some interpretable attributes. So after training this model, we will be able to initially take the CT scans as contextual inputs, feed them through an encoder, which will produce a vector of parameters. And this vector of parameters will be used as parameters of a linear model, which can be applied to interpretable features, for example, specific gene expressions that we can further use to predict mortality of a patient. Right. And importantly, this model can be trained end-to-end. So we'll be able to train the model to make these predictions, as well as along the way discover these sort of parameter like explanations or simple linear models directly from the data. Now, I'm not going to go into technical details again, but I'm going to highlight some of the key results from this line of research. So one of the highlights is that we applied this problem to this approach to a remote sensing problem, where the goal was to predict poverty of different remote areas in developing countries using satellite imagery data as well as additional demographics data. Now we see that by training the model on this data set, sort of end-to-end, our contextual explanation networks were able to find two different submodels or interpretable explanations, some of which were selected and used for areas that were more urban, and some of which were used for areas that were more rural. Similar ideas can be used in other standard benchmarks. And I should mention that oftentimes when we talk about interpretability, we often say that there is some trade-offs that we have to satisfy. The more interpretable the model is, the less predictive power this model should have. With contextual explanation networks, it's not the case. In fact, we're able to get the state-of-the-art results, which is current state-of-the-art on IMDb sentiment classification. And many of the models that were designed afterwards all used large-scale pre-training and external data sets. Our approach used only the given data. So finally, same ideas can be used for survival analysis, trying to predict the mortality of patients that were admitted to ICU. And interestingly, we're able to produce this nice charts that associate different features, different interpretable features that correspond to different patients with the risk or the contributions of these features to the risk of death of the patient over time. And finally, the final highlight is in the area of digital pathology, where we used exactly the same idea applied to discriminative subtyping. And this work was done with the collaborators from our group. So just to summarize a couple of takeaways from this case study, even if we don't have a fixed number of tasks that we're interested in solving from the beginning, we can still try to automatically discover these tasks from the data. And a simple approach that we can use is this parameter generation approach or contextual approach that we used in the case of explanations. So a multitask view allows us to optimize not only for a specific metric, such as accuracy, but also try to balance and discover interpretable submodels for different subtasks that are interpretable and understandable by humans. It leads to no loss in performance, at least in our experience and in all the benchmarks that we considered, and there were many of them. I believe that it is quite useful for a wide variety of applications. In fact, there's been a lot of follow-up work since our paper initially appeared online, not only in the context of interpretability, but also for many other applications, such as machine translation or knowledge graph link prediction, which has been done by friends from CMU. Now, going back to the framework, we started with a question of how to represent multiple learning tasks, right? And I hope this couple of case studies right now give you a taste of how powerful the framework could be, even though the idea is extremely simple. Now, fixed collection of tasks is not all the multitask learning problems that we would like to be able to solve. In the case of fixed collection of tasks, again, we have a fixed number of tasks for which we'd like our model to be able to generalize. But more recently, there's been another very popular setup where we have a distribution of tasks. Or in other words, we have an unbounded collection of tasks. And our goal is to learn a model from a small subset of training tasks in order to be able to generalize to future test tasks that we don't see at training time. Right, so in the learning to learn literature and meta learning literature, this is exactly the setup that we're tackling with. And again, we can construct and represent the setting with the graphical model, an example of which illustrated on the slide. Now, before diving into solving this problem, and of course, we can solve this problem using the same approach that I just described. Take this graphical model, write down the maximum likelihood sort of objective, and try to optimize the likelihood or an approximation to this. However, I'm going to generalize this maximum likelihood principle a little bit more and actually go to variational posterior inference. Right, so in posterior inference, our goal is to infer the posterior distribution over all latent variables given all observed variables. So essentially, posterior is a sufficient summary of all the information and the data that we have under this model about the latent variables in the system. And our goal is to try to approximate this posterior with a variational distribution. So we can't compute the true posterior, it's often intractable, but we can try to approximate it with a variational distribution by minimizing some divergence measure between the two. Now, what kind of divergence measure can we optimize? And there are different options, and we can essentially plug in any divergence measure and try to optimize it. But I'm going to focus on two of them. First, the exclusive KL divergence, and inclusive KL divergence. So in the case of exclusive KL divergence, the problem essentially reduces to minimization of so-called variational free energy. And if we're not interested in the full posterior distribution over the latent variables, oftentimes we're interested just in the point estimate, in which case, for example, when the latent variables correspond to model parameters, it's going to be a point estimate of the model parameters. So this point estimate problem will essentially reduce, or this posterior inference problem under this assumption of point estimate based approximation of the Q distribution will essentially reduce to classical maximum likelihood. Now, interestingly, that if we start optimizing the reverse KL divergence, it gives us another set of algorithms that is not directly correspond to maximum likelihood optimization. Right. So in this case, oftentimes the posterior distribution can be decomposed or factorized into multiple terms that are composed with each other through a product. And in this case, we can try to approximate this distribution also with the product of some variational terms. So this can be done very efficiently in distributed settings using message passing algorithms. And probably, as you would have guessed, in our case, this factorization will correspond to factorization over tasks. So to be, again, much more concrete, I will illustrate why we want to solve why we want to use posterior inference instead of likelihood maximization by looking at the problem of federated learning. So what is federated learning? It's an emerging machine learning problem that has become quite popular in the past 2 years, where the goal is to learn a model from an extremely heterogeneous data set distributed across many, many different entities. And we call these entities clients. These entities could be organizations or mobile devices, etc. And one of the assumptions is that we cannot directly access the data on these entities. Instead, we have to do run some computation directly on these clients and communicate somehow some information to the server in order to be able to estimate the model. So there are two distinct federated learning settings. One of them is called cross-silo, the other one is called cross-device, and we're going to focus in this talk on the cross-device federated learning, where in particular, the setting is such that the number of these clients in the system is extremely large. So it could be many, many millions of clients. And during training, there is no opportunity for us to revisit and interact with the same client multiple times. So not only it is a multitask problem, in fact, it is a problem where we have to deal with this large distribution of tasks, where we learn from each client, from a small subset of clients that participated training time. I'd like to be able to generalize to a subset of clients that we will see in the future. Now, a classical approach to solving this problem is to use distributed optimization, where we'd like to learn a model that will be on average really good for all the clients. An algorithm that is probably de facto standard today is called federated averaging, and this is how it works. So we start with a server and a population of clients. The server would request a subset of clients that will participate in a given round. It will distribute some state or the initial parameters of the model to these clients. They will optimize them locally, return some updates, and then the server will average and apply these updates. And then this process repeats over many, many different rounds. Now, client-server communication is the main bottleneck in this whole setup. It's very expensive to communicate a lot. So to speed up training, oftentimes, and federated averaging essentially suggests that, is clients have to run multiple steps of optimization at each given round, and oftentimes multiple epochs. Right? By running multiple epochs of optimization locally at each round, clients can do more local progress, and as a result, fewer communication rounds would be necessary for the model to converge. So I'm going to illustrate this in a toy example. There are many issues with this approach, and one of the issues is the so-called convergence issue. It's been studied in many, many recent papers in the literature, in federated learning literature. And even in a simple 2D setting that I'm given on the slide for the least squares regression problem, we can see that federated averaging with multiple local steps converges to some point and then eventually saturates and not able to make a progress beyond a certain point. So the fixed point of this algorithm, unfortunately, does not coincide with the global optimal to which we would like to arrive. Now, I'll show you how to fix this by taking, and again, embracing this probabilistic approach. So first of all, we'd like to be able to learn a single model that is shared across all the tasks or shared across all the clients. And the corresponding graphical model for the setup is given on the slide. Now, secondly, if we look at the optimization problem that I just formulated, right, oftentimes these local client objective functions are in fact the negative log probabilities, which essentially corresponds to solving a maximum likelihood problem. But now in this distributed setting, we can't just possibly collect data on the server. Now, we can generalize this problem to variational posterior inference. And as I mentioned before, maximal likelihood is just a special case of variational posterior inference with a specific divergence measure and a specific variational distribution approximation. Now, importantly, the posterior distribution is essentially a product of a likelihood and a prior. And under a uniform prior, the mode of the posterior distribution would correspond to the maximum likelihood estimate. So if we are able to solve the variational posterior inference problem, we should be able to find this global posterior distribution, and then its mode is going to be the right solution. Now, why is this approach better than maximum likelihood? So it turns out that the posterior distribution, in this case, nicely decomposes into a product, right? And in this case, we should be able to sort of solve this minimization problem where we're trying to approximate a product of local posteriors with a product of some variational posterior distributions. Now, this problem can be solved with expectation propagation. That's a very famous message passing algorithm that in this case would correspond to passing messages between the server and the clients. So in our case, we have to simplify this algorithm a bit further because we're in this cross-device setting where we don't visit clients more than once. So this is the simplified version of the algorithm where the first part of the algorithm is very similar to federated averaging, while the second part, where we ask clients to compute something locally, the computation is different from federated averaging. Now, if we use as an approximation local Gaussian distributions, things simplify even further, and we can actually write down this approximate posterior mode in a closed form, which after iterations of this simplified expectation propagation will converge to the following expression. In the end, so this is the algorithm that we can implement in order to actually recover the true global optimum in this federated distributed setting. Right? We would like to compute this mu hat, which is the mode of the global posterior, which can be computed given some statistics, such as local posterior covariances and local posterior means. So the key idea that we're going to pursue here is to estimate these moments of the local posteriors on the clients and then communicate some information about them to the server. And then after that, aggregate and estimate the global optimum. And so there are multiple challenges that we have to resolve. And in fact, these challenges sort of technical. I'm not going to go into details, but we resolve them and eventually come up with an algorithm which we call federated posterior averaging. So surprisingly, this algorithm is extremely similar to federated averaging, where on the server, we essentially run the same procedure, also known as generalized federated optimization. And on the clients, we run slightly, we don't run SGD directly, but we run sort of MTMT sampling. And we use these samples in order to compute these local deltas. So again, just to summarize this algorithm pictorially, a server would again request a bunch of clients at a given round from a population, distribute some state. Now each client will run local stochastic gradient based on CMC, compute slightly different deltas, send them back to the server, and then the server will compute the update to the global state. Now, if we compare, again, the two algorithms on our toy example, we can see that federated posterior averaging with multiple local samples can make significantly better progress towards the global optimum compared to federated averaging. And this is not the case just for the toy example. We tested it extensively in many benchmarks that are quite realistic with very reasonable models such as ResNet 18, which have millions of parameters, and we get a similar result. So in order to be able to train the model in the setting, we first initially pre-train the model using federated averaging. So we'd like to get sort of to a point in the parameter space where our Gaussian assumptions hold. And then after some point, we'll switch basically from federated averaging to federated posterior averaging and enable this local posterior sampling, which improves the loss as well as improves the evaluation accuracy on this specific benchmark. And on some benchmarks that are even closer to sort of satisfying our Gaussian assumptions, such as a stack overflow logistic regression problem, which is convex, we see that the results or the effects are even more pronounced. Now, what is the difference between federated averaging and federated posterior averaging, given that they are so close to each other, right? Algorithmically speaking, they're essentially the same algorithm, but slightly different computation is done on the clients. And to understand the difference, we can analyze them in terms of bias variance trade-offs of the server updates. So we can compute the client deltas and then see what is the bias and variance of these client delta estimates compared to the idealized, right, or centralized update that we could have computed in a centralized setting. And so in the case of federated averaging, as we increase the number of local steps, unfortunately, bias grows significantly while variance reduces. In the case of federated posterior averaging, we start from a larger bias. But as we do more and more computation and produce more and more local posterior samples, eventually bias and variance go to zero. And so if we look at these two charts, there are two ideas that how we can sort of improve optimization. We can improve learning of federated averaging by simply reducing the amount of local computation the algorithm does when it's coming closer to convergence. And in the case of federated posterior averaging, we instead need to increase the amount of computation. So it's puts us in a different regime where we can actually utilize local computation more efficiently when it is available without having to limit it. Now, there's a lot of related work that was trying to address this problem that came out in the past couple of years. And most of this work has really focused on sort of reduction of this bias using different techniques such as regularization and sometimes adaptive learning rates. And FedPA, to the best of my knowledge, is the first approach that tries to take a slightly different perspective. Now, so far I talked about a single model, right? When we wanted to learn a single model that's going to be used for all the clients. Oftentimes, the single model is not optimal for all the clients. We need to have some kind of personalization because for the majority of clients, especially in the very heterogeneous settings, this model may not work well. And the standard approach to doing this is to learn a single model and then to fine tune it on some local data on the test clients if data is available. So it's a two-stage approach and it has advantages and disadvantages. Alternative approach is to take sort of just look at this problem holistically and design a graphical model, again, that represents this personalized learning. And in this case, design a graphical model where we add an additional local latent variable that represents an additional state that each client will try to use in order to sort of optimize its model for its data slightly better, right? And we can formulate now the personalized federated learning problem as simply an inference, posterior inference problem, both for the global parameters as well as these local latent variables. So skipping the details of how we're going to do this local inference, I'm going to present you some results on an MNIST benchmark for personalized learning. So first of all, if we take the standard approach and we look at federated averaging, we can see a huge difference that fine-tuning can make. So we can look at different percentiles of clients on which the baseline model performs really well as clients on which the model does not perform that well. By fine-tuning, we improve essentially for this worst client's performance and get it almost to the median performance. Now, if we simply switch from federated averaging to FedPA, we already see that the global model learned by federated averaging, in fact, is better than the one that is obtained by federated averaging. And even after fine-tuning, the results are quite similar. And finally, if we optimize the model, sort of approach this problem holistically, and run federated posterior averaging for inference of the global parameters, as well as model agnostic meta learning for inference of the local parameters, we see that the best of the results that we can get in this case is for federated posterior averaging plus MAML. So the improvement on this benchmark is not that huge. It's just a couple of percent, but the improvement is there. So I'd like to now summarize this third case study and just give you a couple of takeaways that we can take from this. So first takeaway, which was quite surprising to me, is that Bayesian machine learning and Bayesian deep learning, when we think about Bayesian approaches, we often think about quantification of predictive uncertainty. So as it turns out, it can be useful not just for quantification of uncertainty, but even if we're just looking for a point estimate, using these methods in communication limited settings has multiple advantages. And secondly, federated learning, approaching federated learning from this probabilistic perspective allows us to sort of zoom out a little bit and have a much broader design space of efficient federated learning algorithms. So it allows us to reinterpret federated averaging, as well as design sort of improved algorithm that bridges some of the shortcomings. And hopefully, there will be some connections in the future to Bayesian deep learning, and we'll be able to design new algorithms using this perspective. Now, before concluding my talk, I'd like to mention just a couple of quick things about the final case study that, in fact, motivated and was the original project that I worked on that inspired me to look into probabilistic machine learning as the direction for my thesis research, which is focused on reinforcement learning under non-stationarity. So just to briefly summarize the problem, and here we're dealing with a reinforcement learning problem where we had an environment and an agent, and we're trying to learn a policy for an agent in order to maximize its reward in the environment. The question that we ask is, how do we approach this problem when the environment is non-stationary? Reinforcement learning algorithms are not suitable for non-stationary environments. And in particular, we're interested in a competitive multi-agent domain where we have an agent and opponents playing against each other. So if the opponent is fixed and its behavior is certain and fixed, the agent can simply use the standard RL to outcompete the opponent. However, if it's a multi-round game and the opponent starts, initially is less competent, but over time gains more competence and changes his behavior because of learning or some other factors, unfortunately, this cannot be modeled by standard Markov decision process or standard reinforcement learning problem. So the problem becomes non-stationary. So the key question that we ask here is, how do we account for these potential changes in the opponent behavior from round to round, and how do we learn to play against not just a single opponent, even non-stationary, but against multiple opponents that might change their behavior over multiple rounds. Now, the key ideas that we developed in this work is that we can break up a non-stationary RL problem into a sequence of stationary tasks And the second idea is that multiple opponents can be essentially modeled with the distribution of these non-stationary oral tasks. Right, so just to give you a quick overview, since we've already developed in other case studies, I've already illustrated the key ideas of the framework. Here, we first started with designing a graphical model that describes a distribution of free-form learning tasks. In this case, the tasks are stationary. Then for these stationary tasks, we can derive a policy gradient theorem, and we can show that by optimizing a certain loss function, we'd be able to learn an adaptive policy that would adapt to the subsequent interactions with the same opponent. Now we can extend this to another distribution now over sequences of tasks, right? So we take a non-stationary reinforcement learning problem and we can decompose into a sequence of stationary tasks. And essentially the graphical model for this is again given on the slide. And as a result, using this graphical model, we're able to design a new loss function that allows us to learn policies suitable for non-stationarity. In this case, the key idea was to design a loss function that looks at the experience in the tasks at the previous time step, looks at the experience in the task in the next time step, and tries to find a good initialization for the policy such that after a little bit of fine-tuning, it can work really well at the subsequent time step in this non-stationary reinforcement learning problem. So just to highlight a couple of results in this setting, we designed, this was one of the first works that looked at non-stationary reinforcement learning under non-stationarity, and we've designed a bunch of competitive environments that we're interested in solving using this approach. One of these environments is called RoboSumo, where we have multiple agents of different morphologies that were competing with each other. And the results can be literally summarized in one chart. That the agent that we're learning by optimizing this loss function that was designed for continuous adaptation, in fact, outcompeted and outperformed many other agents across different morphologies, architectures of their policies, etc. Now, this concludes essentially the 4 case studies and the probabilistic multitask modeling framework that I introduced in my thesis. We took a deeper dive into a couple of those, case study 1 and case study 3, and I quickly highlighted some of the results from the other 2 case studies. But the core point is that all of these problems, all these diverse learning problems, we were able to solve them using essentially the same approach. And to summarize the approach, it consists of 3 steps. We started always with breaking up a complex problem into multiple learning tasks. Then we assembled a joint probabilistic model from all these tasks. And we considered 2 types of learning problems with a fixed collection of tasks as well as with the distribution of tasks. Finally, we solved this problem either using posterior inference or as a special case, maximum likelihood optimization. So again, as a result, we were able to design new loss functions that were uniquely suitable for these multitask settings, as well as we pointed out that optimization or distributed optimization in certain settings, such as federated learning, may not be always the best way to go from the beginning. I'd like to point out a couple of limitations of my approach. And just one angle, one particular angle that I'm taking on multitask learning. Right? So one of the biggest limitations of my approach is the fact that it's somewhat manual. Right? We have to design these graphical models, and we have to derive this computation tractable and efficient loss functions. And I think one of the interesting directions to pursue next would be to combine it somehow with AutoML. And so automate many of these steps and perhaps scale it to even more interesting, more challenging problems. Now, the second approach, the second limitation is that almost always we had to know a priori which tasks we are solving. We either know that there is a fixed number of tasks and they have a certain form, or we know that this is a distribution of certain types of tasks. Now, the question is, can we automate that? Can we sort of learn that maybe in some unsupervised way with minimal human involvement? This would be important questions to address. Now, the alternative approach, and I should say probably the elephant in the room right now, is the approach taken by OpenAI with their models, such as GPT-3, which lays at the other end of the spectrum, where there's literally no human involvement necessary. The model is trained entirely in unsupervised way on a massive amount of data, and this multitask abilities sort of emerge automatically. So I wonder which is there a way to bridge the two? And that's one of the other questions that will be interesting to explore in future work. Is it necessary to bridge, or is it not? So I'd like to wrap up with these open-ended questions. So this is just a list of publications that my thesis is based on, as well as a list of some published non-thesis work that I did during PhD. A lot of my work resulted in many open source contributions, and this is just a highlight of some of them on the slide. And finally, well, that concludes the official part of my thesis. I like to say many, many thanks to many people right now. And first of all, I'd like to say thanks to Eric, who's been advising me throughout the last 5 years and guiding my research, and really from the very beginning challenging me to think outside of the box. The product of this research is my attempt to push the boundaries of what's possible, and Eric was always guiding me towards problems that are I'm prone to trying to solve problems in a very abstract way. It was always grounding me in very specific application, and I really appreciate that. I've learned a lot, and I appreciate the research freedom that also got from him. And secondly, I would like to express many, many thanks to my committee, to Peter, Rich, Russ, and Amit. I had a great fortune to interact with every committee member in one way or the other. With some of you, I published papers. With some of you, we organized workshops, and some of you were just chatted about research over coffee. And that was the best of the PhD experience for me the last many years. So for me, PhD was not only about pushing the research and making research contributions, but also building lasting friendships and being part of a large research community. And I think CMU provided that plentifully. So I'd like to thank many, many people who I met, had pleasure to work with, as well as just hang out and discuss research over tea and coffee at late nights and early mornings. So many thanks to great friends, colleagues, and collaborators. And not only at CMU, I was very lucky to be part of other organizations as well, such as Google Research, OpenAI, and had some friends from Oxford that wrote some papers together. It's been a great journey, and I'm really, really thankful to everyone, and I'm thankful for this opportunity to be able to learn so much over the last 5 years. And last but not least, I'm indebted to my family. So many, many thanks to my grandmother. The thesis is dedicated to her, to my parents and siblings, my wife and her family, for all the love and all the support throughout this journey. And now, thank you for your attention. I'm happy to take any questions.
Great, thank you, Maruan. Thank you very much. Okay, as I stated earlier, we will begin with some, open questions from the audience. Any questions from the audience before the committee?